What's up, guys? It's Mr. Bringle, and today we're going to be continuing our discussion on the constant velocity particle model worksheet number 1. We've already done page 1, so if you haven't done that, make sure to do it. And we are now moving on to pages 2 through 4. So here we have a graph, and you see I've already done a couple things here. I just highlighted the object A and object B in different colors. And then I also just circled what's on each axis there because it doesn't actually say a word. So just make sure that you understand that time is on our x-axis, okay, the lowercase t, time in seconds. And then the x stands for position in meters, okay? So we're going to look at this graph and answer some questions about it. So it says, do the cyclists start at the same point? How do you know? If not, which is ahead? Well, we need to look at the y-axis here because the y-axis tells us the position of the objects, right? So it's very clear here that the red object starts down here at 0 meters, and then the green object is starting up at some positive position. So because B starts higher along the y-axis, that means its position is further away from 0. So we can put that in here. If I can type. So green starts ahead of red, or rather B starts ahead of A. We'll do it that way since I'll put this in parentheses. Okay, so green starts ahead of red because it is higher up on the y-axis at 0 seconds. That's just an easy way to word that there. Okay, so now let's look at the next question. At 7 seconds, which cyclist is ahead and how do you know? So we don't actually know exactly where 7 seconds is, but it's probably somewhere, like here or somewhere in this region, right? It really doesn't matter. All we have to do is after 5 seconds, the answer is going to be the same. Whether I asked you 7 seconds, 8 seconds, 9 seconds, 10 seconds, based on this graph, it'll be the same either way. So once again, this is asking us which one is further ahead positionally. So we need to think about the location of the line on the y-axis. So of course, if we go and just kind of trace this up to this point here and this point here and just say that that's at 7 seconds, well, we can see now that the red line, A, has moved past B along the y-axis. So again, if you just wanted to trace these over with a dotted line to the side, you can see that A ends up higher than B, right? So once again, the answer is the same logic here, but this time it's switched. So A is ahead of B. Okay. Okay, so A is ahead of B because at 7 seconds, it is higher up along the y-axis. Okay. Let's make these different colors here, just so we can actually tell what is what. Okay. All right. Which cyclist is traveling faster at 3 seconds and how do you know? So again, this doesn't really matter where I ask you behind 5 seconds. So anywhere, 1 through, really, it doesn't matter the entire time. This whole time I can tell you which one's moving faster based on the slope of the line. Remember, in a position versus time graph, the slope of the line represents the speed or velocity of the object. Because we have position on our rise, we've got time on our run, or distance over time, right? So that is the equation for speed or velocity. And so therefore our slope represents the speed of the object. So all we have to answer here is which one has a steeper slope. That's really what this is asking. Which one has a steeper slope at 3 seconds? And that is clearly going to be A, the red line here. Let's get a new color in here. Okay, so the answer is red because the slope is steeper than green. All right, it says, are their velocities equal at any time, and how do you know? So this one is a little bit of a trick question. The most common incorrect answer ends up being at 5 seconds. People will say that they have the same velocity because they intersect right there. But remember, velocity is determined by the slope, and the slope of those lines never change. The line A has a steeper slope the entire time. So that means it is moving faster than B the entire time, right? And that should make sense because A started behind B and ends up getting ahead of B. So it has to be moving faster. Okay, so I put no, A is always moving faster, steeper slope. Okay, now let's talk about what actually is happening at that intersection of A and B. So at the intersection of A and B, remember vertically along this y-axis here, all that's telling us is the position of the object, however far up along the y-axis it is. So if they end up crossing over right there, what that's telling us is that they're actually in the same exact position. So at this moment right here, and let me circle it, at this moment right here, at 5 seconds, object A is passing object B. So they are right next to each other at the intersection, and then A passes. So it's coming up behind it. This is 5 seconds together, and then it moves past. Okay. So we'll come back down here, and let's get another color here. So So they're at the same position. A is in the process of passing B. Okay. All right. So now this is asking us to draw a motion map for these objects. So let's just start with A, and we'll do it in red since we're going to have to kind of go back and forth because I'm going to need to zoom in here. But let's talk about what it should be. So remember the motion map, we're going to plot the object's motion over a period of time. Each dot will represent a 1 second interval. So we'll start at 0 seconds with our first dot, and the second dot will be representative of 1 second being passed and the new position of the object. Now, this is different than the first page because it doesn't actually have a graph for us to go off of with specific numbers. This one is very vague. What's important here is the difference between your motion maps of A and B. That's what's important. So A starts at 0 meters. B does not start at 0 meters. So there's one difference between them. A has a steeper slope, meaning that it is moving faster than B. So if you remember from the first page, we have to show the length of the arrows to demonstrate how fast the object is moving. So if A is moving faster, it needs to have longer arrows than B, and therefore the distance between the dots is also going to be larger between the dots for A versus B. So I know that's a little wordy. Let's go ahead and show it on the paper here. So I'm going to zoom in a little bit, and let's just remember that A starts at 0 meters, the red one, and it moves faster than object B. So this right here is 0 seconds. Okay. And what I'm going to do is I am just going to, we'll do this. We'll put the next dot here and here, and then the next one would be out here. Now, this isn't going to go all the way out to 10 seconds like this graph, but it's all that's important is that we get the proportionalities correct here. So what we want to do is show this last one is still moving, because if we go back up to our graph, it never tells us that the slope stops. The graph just ends. So we don't want to not put an arrow at the end of that last dot, because if we did that, we're insinuating that the object stopped. For that to happen, that angled line would have to go flat on that graph to indicate that the object has stopped. So we don't want to assume anything here. Let's keep it like that. Okay. So that's object A there. And I'll zoom back in here and we'll get object B on here. So this would be 1 second. This would be 2 seconds. This would be 3 seconds. Okay. Now, we obviously would go all the way out to 10 seconds, but for the sake of this, it's not all that important. Okay, let's move to green now. Now, the green line starts somewhere other than 0, right? It's just not 0. It doesn't tell us exactly where. So it does not matter where you start it on this graph as long as it's not 0. So you can start it right here if you want to, or you could start it ahead of that if you want to. Let's go ahead and start it right there. And since this one is moving slower, notice that the distance between the dots is less. So for the red line, the red dots, I basically, I put 2 ticks in between. But for the green ones, we're only going to put 1 tick in between there. So it looks something like this. Okay. So this would be 0, 1, 2, 3, 4, etc. Okay. So as long as you do that, it's good to go. And that shows me that you understood 2 things here. Number 1, the objects don't start in the same position. And number 2, the object A, or the red one, is moving faster than object B, the green one. Okay. Those are the 2 things that I care about on that. All right. So let's go ahead and take a look at the next page here. And what this has now is it's got the same graph on the left side that we just looked at. And now we have a new graph where object A actually starts way ahead of object B and it now has a negative slope. So let's kind of take a look at what this means. So it says how does the motion of the cyclist A in this graph compare to that of the cyclist A in question 3? So what we're doing is we're comparing the new graph to the previous graph. Okay, so it looks to me like the objects have the same slope, just flipped. So the one on the previous graph is positive, the one on the new graph is negative, right? So what does that mean? Well, most people want to say that it's slowing down, okay, that object A is slowing down because that slope is negative. But that is not correct, because remember, the slope tells us the speed, and that slope is not changing. It is negative the whole time, and it never flattens out. It's not slowing down. So all that's telling us is that object A is now moving backwards. Okay, so in the first graph, object A starts at 0 and moves in the positive direction. And in the second graph, object A starts at some positive position and moves backwards towards 0. Okay, so that's what you're going to want to put in here. So, oops. So object A is now moving backwards from some positive position versus starting at 0 and moving in the positive direction. Okay. All right. So let's move on to the next one here. So how does the motion of cyclist B in this graph compare to the motion of cyclist B in the previous graph? And it does not look like anything has changed. So no change, same motion, okay? And we can kind of see that by lining up the starting position and the ending position. They're in the same spots. It looks like the same slope. Those lines are parallel, slash exactly the same, okay? So now it says, which cyclist has the greater speed? How do you know? And this is referring to the newer graph, the new graph. And so the key here, because most people are going to answer B. Most people are going to answer B and say that it has a greater speed than A because B is a positive slope and A is a negative slope. The catch here is that it says the word speed. Speed does not care about direction, okay? So if I'm walking forwards and then somebody else is walking toward me, we can have the same speed. We can both be walking at 5 meters per second, just in opposite directions, right? So what would be different would be our velocities. Our velocities would be different because velocity includes direction, and we're clearly moving in opposite directions. But we have the same speed. So with this one, again, we're looking for steepness of slope, whether it's steep going up or steep going down. In this one, the slope of A is still steeper than the slope of B, which means that it has a greater speed. If we were talking about velocity, then B's velocity would be positive, A's velocity would be negative, because they're going in opposite directions. So the point here is A has a greater speed because it has a steeper slope. Then I'm just going to put speed does not take direction into account. Okay. So now this next one says describe what is happening at the intersection of lines A and B. And we talked about this in the last one, but it's the same thing. The objects, if we're looking at them on the y-axis, they now have the same position. They're in the exact same spot. So the objects are passing each other, right? Okay. The objects are in the same spot and they are passing each other. Okay, so which cyclist has traveled further during the first 5 seconds? How do you know? So for this one, I'm actually going to pull out let's zoom in on the graph here. So this is asking us during the first 5 seconds, which one has moved further? There's a couple, really, here's all you need to do. Draw a horizontal line to the y-axis from 0 seconds to 5 seconds right here, okay? Now look at the space. Look how much distance B moved. This is what B moved right here, okay? And then this up here is the amount of distance that A moved, right? So obviously A has moved further than B here, okay? Let's get back down here. And let's do this. Okay. So A has moved further during the first 5 seconds. It moved more along the y-axis than B during that time span. Okay. All right, now it wants a motion map for A and B. So let's zoom back out here and take a look at this and talk about what it should look like, and then we'll zoom in and draw our dots on here. So we can go ahead and make B, B can have the same exact motion map that we had on the last one, okay? So let's go ahead and stick with red and green. Red is for A and green is for B, despite what I put up here this. So let me circle these here. So red for A and green for B. Okay. So B has the exact same motion map. It's we already did it, right? So let's just quickly go back and look here. We started it at the first dash there, and then every dash we put a dot. Okay. So let's go ahead and start with B here, and make that same motion map. We'll just start with that this time since A is the one that's changed. Okay. So we'll put B right here, and then we'll put our dots and our arrows. Okay. So this is 0 seconds, 1, 2, 3, 4. Really doesn't matter because it doesn't tell us exactly how long this is going for. But now looking at A, let's kind of go back up there and look at that graph real quick. So what we need to do with A here is we need to start A at a position that's even further ahead than B, because A starts up here, right? A is all the way up here, and B is all the way down here. So we started at some super positive position. And then the key here is that we need to draw the arrows going backwards. It has to go backwards because the object is moving backwards. So we'd want to show that on the motion map that this object starts out here, okay, and then it has, remember, it still has that same slope. So we're still going to go every 2 dashes here with our dots. Okay. And then it does move back to 0 like this. Okay. 0 seconds, 1, 2, 3. But like I mentioned before, it does not specifically say that the object stops moving, right? It just stops at that point. Theoretically speaking, you can have a negative position, so this object could move back behind or into the negative half of that graph. But we'll go ahead and leave it. Just understand that I'm not gonna count you wrong on something like that for leaving it stopped right there. But if it probably should have an extra arrow. Okay. So now what we'll do is just move on to the last page, which is very quick. Just a couple quick questions here. So on this one, we've got Toto and Dorothy are walking along the yellow brick road, and these are their paths, right? So Toto, I'm going to circle in red, and Dorothy, I will circle in green. So it says from start to finish, who travels further? Okay, so who travels further? This is asking us for who has a greater distance, who covered more distance. The answer here is Toto. And the reason for that is that he takes a roundabout path, right? Right, he takes a bathroom break. Okay, goes over by the fire hydrant there. And so he's the dotted line, right? Toto's the dotted line. So Toto is moving all around. He's doing all this stuff, and then he ends up over by where Dorothy is. But Dorothy just goes in a straight line. So clearly that's going to be a shorter distance there. Okay. Now I would ask you though, which one has a greater displacement, right? Greater displacement, or who has the least displacement? Like if I ask that question. So Dorothy has a larger displacement than Toto, even though Toto covers a greater distance, because the distance, the line that's drawn for Dorothy is already the displacement, straight line distance between starting and ending position. The displacement for Toto is the red line that I just drew, the straight line distance between Toto's starting and ending position. So you can see that Dorothy's line is larger, meaning that Dorothy has a larger displacement. However, Dorothy covers less distance. Okay, so that's really what this final question is asking about, is two definitions for how far something travels. Well, distance would be, we've talked before about this term path length. Okay, and then displacement is change in position. Okay, so those are two different ways to measure how far something travels, and kind of demonstrated the difference there. So if you have any questions over the worksheet, please let me know. Otherwise, have a great day.